Hello, hello. Welcome to virtual math with Mrs. Tavares. Okay, so we are going to continue today with lesson 4.2 from chapter 4, which is all about reflections. Now, if you remember, we already learned one type of transformation in 4.1, which was translations. Reflections are just another type of transformation, okay? And what we did in 4.1 translations was moving a figure up, down, left to right. And what we're going to do today is learn about how to reflect images in the coordinate plane. Let's first just review very briefly what it means to translate a figure. So if I had this triangle, ABC, just remember that this is what we would call the image. And if we want to translate this figure, let's say somewhere over here, I need some specific directions about how to do that. In other words, how many units left, right, up, down do I want to translate this image? Which usually comes as a rule written in vector form, vector component form. So it could be written like this, for example, or it could be written as an ordered pair, x comma y, to x minus 4, comma y minus 2. And just remember that this number tells us how many units left, right we're going to move. And then this number tells us how many units up, down we're going to move. And also usually what we have is a vector that we're translating along. So if I wanted to translate if I wanted to translate this image, 4 units left and 2 units down, I would be translating it along this vector here. Vector BD. All right, let's just see what that looks like. So take the triangle, translate it along this vector, and I get triangle A prime, B prime, C prime. So as we can see here, you take point A on the image, shift 1, 2, 3, 4 left and 2 down, and you get A prime. The point on the I made a mistake. This is called the pre-image. Sorry about that. And this is called the image. My fault. Okay, but anyway, so if we take the points on the pre-image and we move them 1, 2, 3, 4 units and then 2 units down, notice we get C prime, which is also the point on the image. Okay, so anyway, that was just to quickly recap what we done last class. Today, what we're going to do is reflections. So I'm just going to create another triangle here, triangle ABC. And anytime we're doing reflections, what we want to do is we're reflecting it over something. Usually what we reflect over is a line, okay? And this line that we're going to be reflecting over, in this case DE, is what we would call the line of reflection. And basically anytime you're reflecting a figure over a line of reflection, if the figure is on the right before, so if the pre-image is on the right, then to reflect over the line of reflection just means it's going to be on the left now, with a little bit of adjusting, okay? Let's just see what it looks like. So if I take this triangle and reflect it over the line, DE, I get this figure, A prime, B prime, C prime. Remember, this is the pre-image, the image before the transformation takes place, and this is the image after the transformation takes place. Now, some important things to notice. C here on the pre-image is on the right side of the triangle, but after it's reflected over the line of reflection, now it's on the left side of the triangle. And this is an important thing to notice because it will happen with figures that we reflect over lines of reflection. The points basically end up on the opposite side. Another important thing to notice is that the size of the shape does not change. So segment BC here is 4 units long, right? And segment B prime, C prime is also 1, 2, 3, 4 units long. So the size of the shape doesn't change after the reflection. Then another important part to notice is the fact that from the point on the pre-image to the line of reflection, we have a distance of 2 units, And the same is true from the from the image B prime to the line of reflection, which is 2 units. And that's always going to be true. If we look up at A and the distance from A to the line of reflection, that's 4 units long. From A to A prime, also 4 units long. Okay? And then the last thing that's important to notice is that if I connect the point on the pre-image to the point on the image, not only are the distances from the point to the line of reflection going to remain the same, but if you notice also, this angle here, I need another point. This angle here that we have, how do I measure? I don't remember how to measure on this thing. It's probably somewhere else that I don't know. Anyways, this angle here is a 90-degree angle. This is a 90-degree angle, 90-degree, 90-degree angle. And that will be true even if I was to change the figure. So if I move point A, it doesn't matter. Connecting A to A prime is still going to, 1, create 90-degree angles, but then 2, maintain that these distances are equivalent. Alrighty, so what we're going to do now is basically go through all of that, but in a more formal way in the note packet. So the title of the lesson you guys can write in your notes. Let's begin. So the diagram shows the reflection of triangle DEF to triangle D prime, E prime, F prime. How would you define a reflection? Well, I think that the easiest way to define it, the simplest way to define it, is that triangle DEF flips over the line of reflection. Okay, and in this case, the line of reflection isn't labeled, doesn't have a name, but it's this line here. Alrighty, couple more. A reflection is a transformation that uses a line like a mirror to reflect a figure. This line is called the line of reflection. Okay, nothing we didn't already know. A reflection in a line M maps every point P in the plane to a point P prime. So maps a point P to a point P prime after some transformation. So that for each point, one of the following properties is true. If P is not on M, then M is the perpendicular bisector of segment P prime. Okay, so in the case where the point is not on the line of reflection, then what happens? So in this case where the point P is not on the line of reflection, then what happens is the line of reflection is going to be the perpendicular bisector of P prime. The line of reflection is going to cut P prime in half and form 90-degree angles. Okay, so we could call this case 1. So in case 1, the point is not on the line of reflection. So what this means is the line of reflection is going to cut segment P prime in half and form 90-degree angles. That's what that means. So point P is not on the line of reflection, then this is going to cut segment P prime in half and form 90-degree angles, which means if I told you that segment P prime was 8 units long, then you know that this is 4 units long and this is 4 units long, just as an example. Case 2 is if P is on M, then P equals P prime. So if P is on the line of reflection, then nothing is going to change. There's nothing that I could flip over if I'm already on the line that I'm supposed to flip over. So if the point is on the line of reflection, So nothing changes. Point P just stays the same. And we just label it as P prime. Alrighty, hopefully not too bad so far. Let's try some actual problems now that we've looked at several notes. Alrighty, so we want to graph the triangle and its image after the reflection described. So as always, let's just begin by plotting these points. We got 1, 3, 5, 2, 2, 1. So that's the triangle ABC. I'm going to just go ahead and graph it quickly on the second plane as well, just so that it's already taken care of. So if I want to reflect for part A, this triangle in the line y equals 1, first of all, what line is that? Anytime that you see an equation which is just y equals a number, y equals some number, could be 2, could be 5, could be -3, -2. Anytime you have y equals a number, it's going to graph as a horizontal line. Running out of space. As a horizontal line that will pass through the y-axis, or will pass through a y value of 1. Okay, so here's a y value of 1. I'm just going to draw a horizontal line through y equals 1. Obviously, that's not perfectly straight. Let's pretend that it is. So if I want to reflect over this line, right now, most of my points are above the line. When I reflect them, they will all be below the line, but equal and distant from the line of reflection. So if I look at A, point A on the image, on the pre-image, sorry, it is 2 units away from the line of reflection. So its image after the transformation, after the reflection takes place, will also have to be 2 units away from the line of reflection, but on the opposite side. So from above to 2 units below. So right there is where A prime would be. Whoops. Right here is where A prime would be. And the same is going to be true of B. B is above the line of reflection and 1 unit above, so B prime is going to be 1 unit below. And then C, since it's on the line of reflection, C prime will also be on the line of reflection at the same location. We just relabel it C prime, and there's your triangle ABC. Next, in problem B, I want to reflect it over the line x equals y. Now, if y equals a number gave you a horizontal line, what would you guess x equals a number would give you? You got it? A vertical line. So anytime you have x equals a number, that will always graph as a vertical line, and it will pass through an x value of 3. So go to the x-axis, find 3, and just graph a vertical line through 3. Now this one is going to be a little bit more complicated only because it's passing through the triangle, but that's fine. The idea, the concept is still the same. If A is on the left of the line of reflection, then A prime is going to be on the right of the line of reflection. If A is 2 units away from the line of reflection, A prime will just be 2 units away from the line of reflection. Same for C. C is 1 unit away from the line of reflection and on the left, so C prime will be 1 unit away from the line of reflection, but on the right. Same thing for B. B is on the right of the line of reflection, so B prime has to be on the left of the line of reflection and 2 units away. So this is where B prime is. And that is your figure. One more thing that I want to mention is the fact that the distance from the pre-image to the line of reflection is the same as the distance from the image to the line of reflection. But also to make a note about the fact that connecting the point on the image to its corresponding point of the pre-image creates 90-degree angles. This is going to be important in the next problem that we see. We're not going to do this one. This one we're going to skip, and I'll have you guys do this for homework. All right, example 2. graph segment FG, which has those endpoints, and its image after reflection in the line y equals x. So let's graph it first. That segment FG. And I want to reflect it over the line y equals x. Now, hopefully you remember from Algebra 1 that that's a linear function or equation, and it's actually in the form y equals mx plus b. Because there's no number being added or subtracted to the x value, that means our y-intercept is just 0, and the slope in this case is 1. So we're going to go up 1 over 1. So y-intercept of 0, 0, up 1 over 1, up 1 over 1, up 1 over 1, so on, and in the opposite direction as well. So that is the line y equals x. Now this one is a little bit more complicated because I know that these points are above the line of reflection, so I want to go below the line of reflection. But how exactly? That's where it gets maybe a little tricky. So, if point G is above the line of reflection, G prime has to be below the line of reflection. But I can't just put it wherever, right? Because then this distance here is clearly not equivalent to this distance here, right? So how I do it is I try to almost mirror, right? Reflections, mirror the distance or the location of G to the line of reflection, and do the same thing for G prime, but just on the other side. So I'm noticing here that G to the line of reflection is like almost diagonal across the box and half of the box. So I'm just going to do the same thing, but on the other side, and that's where G prime would be. Now, remember, do these distances look the same? Yes, and they need to be the same. Secondly, does it look like these are 90-degree angles? Yes, and that's the second thing that has to be true because G is not on the line of reflection. Let's do the same thing with F. F to the line of reflection is like a diagonal and a half of a box, so F prime should be diagonal and a half. So that's F prime. Then, another thing that I could remember is this length here from F to G is 2 units long, and this length here from G prime to F prime is also 2 units long. So, I know I did that correctly. That can be hard to do by hand. It is a little bit more complicated. So what we're going to see now is actually some rules, some formulas that we can memorize that would help us perform these reflections a little bit easier. So the first case is if AB is reflected in the x-axis. Okay, when that happens, A comma B becomes A comma negative B. So in other words, if I had 2 comma 3, that would become 2 comma negative 3. My x value stay the same, but my y value is going to be the opposite sign. If you had a reflection in the y-axis, then what happens there is the y value stays the same, but the x value becomes the opposite sign. If you have a reflection in the line y equals x, what happens there is that the ordered pair is going to swap. So if I have 2 comma 3, that would become 3 comma 2. So swapping your x and y values. If you reflected over the line y equals negative x, not only do you have to swap your x and y values, but you also have to make them the opposite signs. So if you had 2 comma 3, what that would become is negative 3 comma negative 2. So that's another way that you could do these reflections, just following these rules if you prefer that. Some people are more visual and they could just figure it out by looking at the figure. Others like rules, whatever you prefer. So if I want to graph this segment again, but this time reflect it over y equals negative x, I have 2 options. I could do it visually like I did here, or I could just use the rule that it corresponds to from this list. So let's do it both ways. So first I'm just going to graph. I don't know if that's right because I don't remember. Good. Alrighty. what is the line y equals negative x? Well, that has a y-intercept of 0, 0, and a slope of -1. So it's basically the same as the previous problem, except it's going to have a negative slope, so it's going down from left to right. Now, again, you could do the same thing that we did before, which is just count boxes. Or you can use this rule, because I'm about to reflect it over y equals negative x. So actually, let's just do it that way. If f is located at -1, 2, then according to the rule, f prime should be located at the point where I flip these and make them the opposite sign. So flipping it, I get 2, -1. Making them opposite signs, I get -2, +1. -2, +1. So that would be f prime. It's looking like it's correct. G is located at 1, 2. So according to the rule, I'm going to flip my x and y values, and then I'm also going to make both of them the opposite signs. So -2, -1. And I don't know about you, but that looks pretty good. And that would be the answer. Lastly, it says to verify that f prime, that there should be a line above that, segment f prime, is perpendicular to y equals negative x. Now, in order to verify that, I'd have to construct the segment, and I'd have to find the slope. We already know that the slope of y equals negative x is -1. To find the slope of f prime, segment f prime, I would just count boxes. So up 1, over 1. So I have a slope for f prime of +1. And we already know y equals negative x has a slope of -1. So because they're opposite reciprocals of each other, we know that the lines are perpendicular. So that is correct. We just verified that. Alrighty, moving on. We kind of already discussed this, but let's just highlight it. A reflection is a rigid motion. So remember, that means that the size of the triangle is not going to change after the reflection. If segment EF is 2 units before it's reflected, segment E prime F prime is also going to be 2 units after it's reflected. So that's what this is all referencing to. Nothing too crazy. Now, just like in 4.1, where we did multiple translations at once, now that we know 2 types of transformations, we are going to complete or perform more than one transformation in a given problem. So a glide reflection is when we do a translation and then a reflection. So nothing too crazy. We're just going to take it one step at a time. Example 4. We're going to graph the triangle. We're going to translate it using this rule. And then we're going to reflect it using this rule. So let's just begin by graphing the triangle. We have 3, 2, 6, 3, 7, 1. So there's my triangle. Now the first thing that I want to do is I want to translate this triangle. 12 units left, and I don't want to move it up or down. Remember, if I wanted to do that in component form, that would just be -12, 0. I am taking this figure, and I'm sliding it 12 units to the left. Actually, I'm probably just going to do that. So this, I'm just going to kind of cheat the system here. I'm going to copy my triangle, and I'm going to paste it. So if I shift this 12 units to the left, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 units to the right. Sorry, left. Good. So that is after the translation. Now I want to reflect it in the x-axis. So let's draw the line of reflection, right? So that would be y equals 0. That's the line I'm reflecting over. And I'm going to cheat the system again. I'm going to paste this. Actually, I don't know if I'll be able to do that. I wanted to see if there's a way. No, I don't think it's going to work. If I could flip it over. Okay, it's not going to work. I guess I'll have to do the math. Alrighty, so I'm going to take all these points. They're above the line. They need to go below the line, but maintain their distance from the line of reflection. So A prime is just going to go here. C prime is going to go here. Now for B prime, I actually want to use these rules just to show that they work. So if I'm reflecting the x-axis, I keep my A and B values the same, but I make my y value the opposite. So what that means is B is currently located at -6, 3. Ooh. So B prime, I'm going to keep my x and y values as is, but I'm going to make my y value the opposite sign. So because it was positive, it becomes negative. So -6, -3, and there's B prime. Oh, sorry, it shouldn't be B prime. What am I doing? I forgot. I cheated the system and I messed up. This is B prime, this is A prime, this is C prime. This is A double prime, C double prime, B double prime. It doesn't really help when I'm recording this because I don't have you guys to tell me that I'm making mistakes. Anyways, let's keep on going. So one thing that's kind of cool about reflections is the fact that there are figures that when you reflect them onto themselves show this symmetry, this symmetric nature. So a figure has line symmetry when the figure can be mapped onto itself by reflection in a line. And this is what we call the line of symmetry. So if you notice, this is the line of symmetry, and this butterfly has line symmetry because this right side of the butterfly will fit perfectly on the left side if we were to reflect them over. Think of it as like folding it in half, and the two sides just fitting perfectly together. That's all that means. So for this last example here, we're just going to see if we can figure out the line symmetry of each figure. And not every figure is going to have line symmetry, but some will. So if you look at the figure, just think of, is there a way that I could fold this figure in half? Not necessarily it has to be right down the middle, but could be from left to right or diagonally, so that the left side and the right side, or the top and the bottom, will fit onto each other perfectly. So for this figure, if I was to try and draw a line like that, the top and the bottom wouldn't fit perfectly. But if I do this, right, this right side and this left side will fit perfectly. So that would be the line of symmetry for the trapezoid. And that's actually the only line of symmetry. Now for a regular hexagon, there's actually quite a few, because all these lengths are the same. Regular means all the sides are the same. All the sides are congruent. And so there's actually going to be a lot of line symmetry here. So you could try it on your own if you want. Pause the video, see if you can figure it out. But if I go like this, again, this right side is going to fit perfectly. Left side is going to fit perfectly onto the right. I could do it like this, right? Flipping the bottom onto the top would fit perfectly. There's a lot more, actually. I could do this. Okay, again, notice top and bottom are going to fit perfectly. And if I could do that, then that means I could also do this. Right? It's hard to see when you have so many lines going through it, which is why I'm erasing them so you can see it one at a time. But that's the idea. I'm writing all the lines. I could also do this. Right? See it? And lastly, I could do this. And that would be all the lines of reflection. There's 1, 2, 3, 4, 5, 6 lines of reflection. Last one. We've made it. That definitely wouldn't work. Nor would that work, because this is on the top, so the point that corresponds to it after the reflection would have to be somewhere up here. So not that. What about this? Would that work? No, if I reflect, it would have to be somewhere here, not here. So this guy has none. That's sad. That's a weird smiley. This guy has no line symmetry. And that's it, guys. That's the end of the lesson. So I hope things made sense. Please write down any questions you have, and we'll go over them when I'm back. And that's it. I hope you guys enjoy the rest of your day.